I think a lot of students are really intimidated by spherical coordinates just because of the choice of letters that we use, rho and phi and theta. So don't fall into that trap. I know that these are new and strange symbols, but it's really not a big deal. And we really do need spherical coordinates. Spheres are just terrible things to try to integrate using rectangular coordinates. There's just every way that you look at a sphere, any way you draw a line, it's going to intersect the surface twice. So this is a necessary thing. It's not mathematicians' fault that it exists. People engineer things with spheres in them. Spherical coordinates uses two new Greek letters, rho, and then this one here. You can either say phi or phi. I guess you should probably say phi because most of you would call this symbol pi. You can actually call that one pi or p. So since we call this one phi, we should probably call this one phi. I don't know though. I mean, I've been calling it phi my whole life, so I'm probably going to keep calling it phi. Yeah, so what are they? So rho, not to be confused with r, is the distance from the origin out to the point. So that distance right there in 3D space, that is rho. Unlike r, so remember that r is this distance right here in the xy plane, just that distance, it's a 2D distance. So that's the distance between, that's the difference between rho and r. Rho is the 3D distance, r is the distance to the shadow of the point. Okay, now about phi there. So this is probably the #1 place for confusion amongst students about the definition of phi. The definition is as the angle opens down from the z-axis, okay? So if here you have the z-axis, okay, and then this line is this line down here. This line down here is the line that makes an angle theta with the x-axis. That's that line right there. So if you have some ray that extends out right here, this angle down from the z-axis, that is phi. Okay, so it doesn't open up. I know that we're used to things opening up, but this one opens down. It is actually natural in some sense for it to open down. But as long as we're here pointing this out, I just want to make the point that so phi equals 0 points straight up right there. There's phi equals 0. That's just straight up the z-axis. And then right here, this direction right there, that's going to be phi is equal to pi over 2. And then the one that points straight down here is pi. So the issue is that if we go past pi, if we rotate like all the way over here and we go some direction in that way, then that's actually the same as opening in this opposite direction, except extending out a negative radius. So because of that, it's just our convention. Usually we imagine phi as being between 0 and pi. It doesn't have to be. If you want to, you can break that convention and go all the way into, down past the negative z-axis. It's just a little bit weird to do it that way. There are ways to arrive at the correct answer, but it just kind of leads to mistakes about double counting area, and including some negative radiuses. So let's just, kind of keep it simple here and just keep phi in between 0 and pi. The easiest way to change from rectangular coordinates to spherical coordinates is to kind of go through polar coordinates. So let's start by looking at this plane right here. I call it the theta plane. Okay, hopefully you can see from my drawing that this plane is perpendicular to the xy plane and it makes an angle theta with the x-axis. Okay, so let's just start labeling the pieces of information on this plane. So some of them are kind of obvious. The first one is the distance from the origin out to the point. That's this distance right here. Okay, that's going to be that kind of diagonal in the plane right there. So that's rho. Okay, the next one is also pretty obvious. This distance right here is z. So I put it right there on this wall. Actually, the way that I have it drawn here is actually over here, but this thing is a rectangle, so the z goes on either side. And then, so we also have this distance right here. That's the distance from the origin out to the shadow of the point. So that's r. So, you know, also again, because it's a rectangle, I can also put the r up top there. Okay, and now the last one, phi. So phi opens down. I'm never going to shut up about this. Okay, this angle right there is phi. I know everybody wants to make it go up. That's very normal to us, but that's not the definition. So I put phi right there in that corner. All right, so this is it. Once you draw this picture, the rest of this just falls right out. Hopefully you can see by looking at this that I do have a right triangle here. So I can just apply SOHCAHTOA to this triangle, and that is going to spit out the change of coordinates formulas. Relative to phi, okay, phi is down here. Relative to phi, r is opposite phi, and z is adjacent to phi, and rho is the hypotenuse. So did I do this right? Okay, so the cosine should be the, I did, see, adjacent over hypotenuse right there, okay? And then likewise, sine is going to be opposite over hypotenuse right there. Okay, so that's it. We're done. We have successfully changed coordinates. So you can see actually if I multiply both sides of this equation by rho, I'm going to have z equals rho cosine phi. So I'll just put that, z equals rho cosine phi. Okay, and now this one says r is equal to rho sine phi. So I can just replace these two r's with rho sine phi from that coordinate right there. And that's it. So it's going to be rho sine phi cosine theta. And then y is going to be rho sine phi sine theta. So that's it, you know, basically the kind of symmetry that I see that helps me memorize these formulas is, you know, you got a rho out in front of all of them, and then both the x and the y depend on the sine of phi, and then the z depends on the cosine of phi. That just makes sense to me, you know, like when I look at this distance right there, that looks adjacent to me, and when I look at this distance right there, that looks opposite to me. So that's how I change the formulas. Oh, now we have to do the volume differential. I've written here again this formula for the arc length of a sector. So this is really just S equals R theta, except this time what we're going to do is we're going to imagine the point moving down a little bit and that being produced by some little change in angle there, d phi. So now I've put d phi right here in the corner, and then now since we're in spherical coordinates and this is a 3D distance right there, I've put d rho. Okay, so that's the only thing that's different about this from as opposed to like cylindrical coordinates or polar coordinates. Okay, so now, so we were like at this point right here, and then we went out a little bit extra, and that produced this dimension on that box right there. So that means that the way that we went out a little bit more is we changed the radius. So that means this distance right there is going to be d rho. Okay. Now, just like before, this distance along the bottom right there, that comes from changing theta a little bit, and its distance over to the origin is still r. So just like in polar and cylindrical coordinates, this length down on the bottom there is going to be r d theta. Okay, but that doesn't help us because we don't have r's in our problem. So remember, r is equal to rho sine phi. So this distance right here is really rho sine phi d theta. And then there's just one more. That's this height right here along the side of the box. Okay, so that comes from making a little angle right there, d phi, opening a little d phi. So that's really just this picture down here. All right, so that's it. Congratulations, we made it. That means that this distance along the side here is going to be rho d phi. Okay, so the volume differential dV is just the volume of that little box right there. Well, yeah, that little box right there. Okay, so all I need to do is just multiply all these things together. So here are the three things that I am multiplying together. So hopefully you can see that I've got a rho squared there, and then a sine phi, and then all those little differentials at the end. So the sort of traditional way to write this, I guess Fubini's theorem tells us it doesn't matter, but so we're going to put here rho squared sine phi d rho d phi d theta. And that's it. Here is our new volume differential. You know, I know that it's a bit of an ugly formula, and you may not necessarily want to reconstruct this theory every time. So there's going to be a bit of a memorization when it comes to spherical coordinates. Let's set up some examples and calculate some volumes. I got to start off with the like most basic example so we can just make sense of this. And this is also an explanation as to why we really need spherical coordinates. Let's try to use our laser beam method to find the volume of this in rectangular coordinates, and you're immediately stuck, right? I mean, there is just no way that you can draw a laser beam that it doesn't enter and exit at the same surface, okay? So, you know, rectangular coordinates are just terrible for calculating. I mean, even if I did like, dy's or something that way, it doesn't matter. It always enters and exits. So we're gonna have like crazy pluses and minuses and a bunch of really ugly square roots. So let's try to use this in spherical coordinates. Okay, so here's how it starts out. This is basically, hopefully when you look at this and you know the volume differential, basically what I've just set up is the integral of 1 dv, and then all of this right here is dv. Okay, all right, so let's talk about these limits of integration. So the first one is if we imagine a ray starting at the origin and extending out, then this ray does start inside the figure. So we're going to go from rho equals 0 out to the radius. So that's where rho equals rho. And then the next one is phi. So, you know, I already introduced this, but phi opens down in this direction. So all I'm going to do is pi of it. So when I do phi goes from 0 up to pi, what that means is I have essentially made this half disk right here. Okay, that's what these two limits of integration mean. Now, if you take a half of a disk and you rotate it all the way around, right, there's the half of the disk, and you rotate it all the way around, that is going to make one complete sphere. Okay, so this means theta is going to go from 0 to 2 pi. Okay, so there we've done it. And this is, you know, this is really traditionally a very natural way to set up objects, you know, is to end up with these limits of integration and spherical. So if you're trying to work with like a whole sphere, you know, just get used to this setup right there. That's basically as big as those angles could ever be. Okay, so let me just work out this integral off camera and spit out the final answer. Okay, so it falls out pretty nice. So what's going to happen when we do this? So the first thing is when you do an antiderivative for rho squared, you're going to add 1 to the power and divide by the result. So that's where you get those two 3's right there. Now, when you do an antiderivative for sine, you're going to get negative cosine, and then you're going to plug in 0 and pi. So that's going to give you like a minus negative 1 there. So that's going to give you 2. And then all of this is just independent of theta, so then you're going to multiply by 2 theta at the end, so that's where you get that 4 pi from. And there it is. So this formula is working. We are correctly, this is right, by the way, from geometry. So we are correctly calculating the volume of a sphere. I always kind of find this funny because basically, like, this is supposed to be a commercial for how good spherical coordinates are. So it's like, look, instead of memorizing this formula, you can just memorize that formula right there and it'll save you all the trouble. And then instead of just memorizing the volume of a sphere, you can just work out this integral every time. Just no problem, right? God. I call this the drumstick problem. You know, those like cheap ice cream cones that you get from the grocery store. So what we're asked to do is find the volume of the solid that is above this cone and below this sphere. So the first thing is I drew this I drew the objects, and then this is the cone that we're talking about right here. And just to be clear, it's not flat on the top. It's not flat on the top. There is, here is the flat, that is the circle that would be the top of the cone. But then there is like a little distance along the top there that is just the like little cap of the sphere up above it. Okay. All right, so let's just jump right into this. We're asked to find the total mass. Oh, I didn't give us a density, the total mass, and let's say the density is delta equals, let's do x squared plus y squared plus z squared. Okay, let's find the total mass. So I'm going to set this up as a triple integral of delta. So delta is going to be rho squared. Hopefully you can see that. That's obvious, right? That's just the distance from the origin out to a point. So the density here is rho squared, and then I've got to put this volume differential at the end. So there's another rho squared sine phi d rho d, so phi d theta there. All right. So what about all these limits? So now I'm going to imagine a ray starting at the origin and emanating out. Okay, so since the ray starts inside the solid, I'm going to start at rho is equal to 1. Oh, sorry, start at rho is equal to 0 because I start inside the solid, and then it's going to exit right here at rho is equal to 5. That's the radius of this sphere. Okay, now let's worry about phi in a minute here. We are doing all the way around. It is the entire drumstick here. So it is going to go theta is equal to 0 out to theta is equal to 2 pi because it goes all the way around like that. Okay. All right, now we're going to need to figure out what the range of phi's are. So let's look at the picture like this. Okay, and this amount of angle right there is going to be phi. So it's definitely going to start at phi is equal to 0. And the last thing for us to work out is how far out does it go? Some of you may be in the place where you can just look at this and see automatically that makes a 45-degree angle right down the middle. But let me show you how you could get that if you didn't just see it right away by looking at it. I look at this formula right here, right? That's what's going to make this wall and this wall right here. So this is complicated because it has both x's and y's in it. So what I'm going to do is I'm just going to consider this slice right here, which is just, it's just like this little piece of it. And then, so that is basically where x is equal to 0. So actually, I messed it up down here. If x is equal to 0, then z is going to be the square root of y squared, which is the absolute value of y. So that's what I've drawn right here. This is z equals y, and that z equals negative y. So you end up with this picture, which is z is equal to the absolute value of y. Okay, now you can always get a point on this line, right? The formula is z is equal to the absolute value of y. So you can pick any value of y that you want, and you just take its absolute value, and that gives you z. So that means that there is a point on this line, 1, 1. Okay, so remember that phi is the angle that opens down. So if you look at, you got a kind of picture here. Okay, and you got an opposite and an adjacent in this picture. So actually what you can conclude from this picture right here is that the tangent of phi is equal to TOA, the opposite, that's 1, divided by the adjacent, that's 1. Okay, so what we know is that the tangent of phi is equal to 1 divided by 1. Okay, so, I mean, if I haven't convinced you that it's 45 degrees yet, then let's ask the calculator. Okay, so I'm just going to make sure that it's in degree mode. And then what you can just do is just a quick little tangent inverse of 1 divided by 1. And that will give you 45 degrees. So that was the logic that I used to come up with this pi over 4 right there. Let me cook up another scenario, another cone, and give you a little puzzler to try to figure out what this angle is. But this is really the content right here. That's really how you set these up. You just kind of got to do some thinking about what the shape really looks like that you're dealing with. Then you put the density on the inside, you put those DVs, and then it's just this kind of like laser beam method, and you're just looking for ranges of angles. Okay, so here's just a little bonus puzzler. Let's see if we can find the angle phi for this cone. Z is equal to 3 square root of x plus 3 square root of y. Okay, so just like before, I'm going to pick x equals 0, and then this is actually the yz plane, and I end up with this equation right here. Z is equal to the square root of 3 times the absolute value of y. So I can pick any y that I want, so I'm going to pick y equals 1, and then z is going to be the square root of 3 times the absolute value of 1, which is the square root of 3. Okay, so that means this distance right here is 1, and that distance right there is the square root of 3. So then the tangent of phi is equal to TOA, right? So it's going to be the opposite divided by the adjacent. So the tangent is going to be 1 divided by the square root of 3. Okay, brilliant. So this means that I can just use tangent inverse to get this angle. So I did the tangent inverse of 1 divided by the square root of 3, and I got 30 degrees. So I'm going to put pi over 6 right here. And here's just a quick question. Hopefully you can start to see through this. What should I do for z equals what if I wanted to make it pi over 3? What if I wanted to make it like a 60-degree angle inside there? Then what could you do? Hopefully this takes the edge off of spherical coordinates. I know it can be a little bit intimidating, but the best thing to do is to just jump in there and start trying those homework problems, and try to use your resources, and reach out to me if you get stuck on any of these problems.